Let's take a journey to the very beginning of time. What was the Big Bang actually like? And where did we come from? And the stars and planets and our atoms, where do they come from? What's the end of the universe going to be like? We'll discover all of that and more in this Timeline of the Universe series. Now, approaching the very limit of our understanding of the universe is the Planck epoch. Beyond the Planck scale, scientists using conventional ideas and Einstein's equations can no longer explain what happens. They need to use quantum effects. But t=0, or the singularity, is just a mathematical placeholder for this is where our conventional ideas end. So don't think of the Big Bang as the beginning of time necessarily. Think of the Big Bang as the end of our understanding of space and time. Now at this time, about 10 to the negative 43 seconds after t0, the universe was about, on average, 10 to the 32 degrees Kelvin in temperature. Okay, that's extremely hot. The universe was extremely dense, extremely small, smaller than the size of a proton. Now, at these extreme scales and temperatures, scientists think that all the four fundamental forces of nature we know today, the electromagnetic force, the weak nuclear force, the strong nuclear force, and gravity, were all combined into one unified super force, where essentially mathematically they are all symmetrical. In other words, you can't mathematically distinguish one force from another. Some scientists believe that because of the quantum effects, the fabric of space and time itself was fluctuating so much that it actually was more foamy. It wasn't smooth and continuous like it is today. But again, we need to understand quantum gravity to understand what happened at this time, about 10 to the negative 43 seconds after t0. From this point to about 10 to the negative 36 seconds is the Grand Unification epoch. This is when the universe begins to expand and cools down to about 10 to the 29 degrees Kelvin. But as the universe expands and cools, gravity is one of the first fundamental forces to separate from the other three. The other forces, the strong, weak electromagnetic forces, remained unified during this time in something called a gut force. Now, during this time, the universe was filled with a soup of exotic particles and antiparticles, and X and Y bosons. There were no electrons yet, or quarks even, or even photons. Photons didn't exist yet because the universe was just too hot for those things to remain stable and distinct. It's also important to understand that in quantum field theory, all fundamental particles with their each distinct quantum fields existed, even since t=0, right? The quantum fields always existed. It's just that the particles would be excitations of these fields. And so when we say there's a unification of forces, what we mean to say is that the particles that mediate the forces, like in the case of the electromagnetic, the photon, and the others, what we're saying is that their corresponding quantum fields were at very similar energies, and so they're indistinguishable from each other. That's all that really means. So these quantum fields fill up the entirety of the universe. Every fundamental particle has a corresponding field that extends throughout the entirety of the universe, even if it's infinite. And so because the universe during this time was super hot, these quantum fields are going to be at higher energies, allowing for a soup of particles to pop in and out of existence. You're going to have antiparticle-particle pairs popping in and out of existence, and certain perhaps X and Y bosons, hypothetical exotic particles during this time. And from this point to about 10 to the negative 12 seconds after t=0 is the electroweak epoch. And this is where the bang happened in the Big Bang, the rapid inflation, right, with the scale factor of expansion of like 10 to the 26. The universe cooled even further, and we see the freezing out of the strong nuclear force. Now, many scientists agree that the inflation of the Big Bang was sparked by an inflaton field, which permeated all of our universe, but there was a point of extremely high potential energy density that, due to a quantum fluctuation, produced a ton of negative pressure on our universe and literally caused our space and time itself to inflate really rapidly. The random quantum fluctuation of the inflaton caused its potential energy to be converted into kinetic energy. So now at this time, the observable universe is about the size of our solar system, and it's about 1 quadrillion degrees, which is cold enough for the strong nuclear force to separate from the others. And now we see gluons. Gluons are the force carriers of the strong nuclear force, which bind quarks together with neutrons and protons. Now here we start to see some of the first force-carrying particles for the electroweak force, like the W and Z bosons and the photons, but they're both massless and indistinguishable from each other. And this leads us into the Quark epoch. The Quark epoch begins about 1/trillionth of a second after t equals 0, and the universe expands and cools for about 1 quadrillion degrees to an average temperature of about 10 trillion degrees. And by this time, the universe is about a few light years in diameter. The universe cools enough for the third force in nature to finally break apart from the others. Symmetry breaking finalizes, and now we have 4 distinct fundamental forces in nature. The universe is also cold enough for the Higgs field to finally activate for the first time, and now particles start to gain mass. Think of the Higgs field like a sombrero, where the peak of the hat is where the Higgs field was at, where the temperatures are really high, which is bouncing around that area. But as the universe cooled down, the Higgs field could settle down to the lowest energy state, the brim of the hat, and it could settle there. And this is where particles that interact with the field now gain mass as they move through it, kind of like molasses. Kind of like when you move through it, you gain that drag. Some particles didn't interact with the Higgs field, hence they remain massless. The universe was also cold enough at this point for free quarks to emerge, with the gluons and other photons mixed into this quark gluon plasma. Think of it like a boiling pot of water where you have little bubbles coming in and out. Just like quarks and anti-quarks would pop in and out of existence, come in, annihilate each other, and then come back out. And it's around these temperatures, 4 or 5 trillion degrees, where scientists are growing now in confidence and certainty as to what's happening at these times, because we have particle accelerators that can measure directly these types of temperatures, 4 trillion degrees. This leads us into the Hadron epoch, where finally temperatures get to around 3 trillion degrees Kelvin. This is a critical point, where quarks begin to confine and become distinct particles, and they grow into these particle pairs, anti-quarks and quarks. This is when the strong nuclear force becomes strong enough to bind these quarks together into particle pairs instead of them freely flowing in this quark gluon plasma. And now those quark pairs or trios are able to form things like neutrons and protons, things we're made of. And by this time, the universe is filled with radiation, it's filled with gluons binding together to form quarks, forming neutrons and protons and their antimatter counterparts, antineutrons, antiprotons. So the universe now filled with quarks spontaneously creating these protons and neutrons constantly that annihilate each other. But about 10 to the negative 4th seconds after t equals 0, the universe becomes too cold for these quarks to continually make these new neutrons and protons. So as hadron and antihadron production slows down, we're left with all we have left. However, there was still this battle going on throughout the universe between hadrons and antihadrons. They were still annihilating each other. In fact, during this time, almost all protons and neutrons and their antimatter counterparts were all destroyed, except for a very few remaining protons and neutrons. And we don't know why the antihadrons lost the battle. Obviously, they're gone for the most part, right? What's left is just the stuff that makes us up. But it's possibly because there is an initial imbalance between the antimatter and matter. There is a bit more, regular hadrons versus antihadrons. And now the universe is 1 second old. All that happened in 1 second. Now the universe is mainly composed of a sea of dense photons in the form of X-rays or gamma rays, as well as the few remaining protons and neutrons. The universe continues to expand and cool down to about 10 billion degrees Kelvin. If you were to travel back in time to this moment, you wouldn't be able to see anything except for this glowing coming from the plasma from all those photons. You couldn't see through space or cross space because there wasn't enough empty space for light to travel through, because all this light would just be bouncing off of other particles in this dense soup of stuff. All you would see is just this glowing universe at all points of the universe. There was literally no darkness at this time, just glowing plasma everywhere. Neutrinos were also caught into this mix, where they were just crashing into particles all around. But these neutrinos were also at the same time converting neutrons into protons and protons into neutrons. They can do that. However, neutrons have a bit more mass than protons, so it takes more energy to convert a proton into a heavier neutron than energy it takes to convert a neutron, which is heavier, into a lighter proton. However, because these neutrinos were just bouncing around everywhere, they had enough kinetic energy to convert all these things in roughly equal amounts, protons, neutrons. Until the universe continued to expand and it was too cold for neutrinos to convert protons to neutrons anymore. Now more and more neutrons are being converted to protons, and now there's more and more protons and less neutrons. Well, the universe continued to expand, and thankfully, its density decreased enough for those neutrinos to finally freely escape away into the universe. And they were no longer bounded to that plasma, where they were bouncing off of neutrons or protons. So all in all, we were finally, thankfully, left with about a proton to neutron ratio of about 7:1. So for every one neutron, there were 7 protons. Thankfully, we didn't lose all of our neutrons. Because if the universe didn't continue to expand and that neutrino decoupling never happened, we would have no more neutrons left and we wouldn't exist. Now, really interestingly, scientists predict that there is this cosmic neutrino background that we could potentially observe. However, their energies are so small that current technology has no ability to detect these neutrinos. But we predict that it's there. We can see those neutrinos from that first second of the universe. And this leads us into the late Lepton Epoch. 5 seconds into the universe, it expands to a few hundred light years across, and it cools down to about 1 billion degrees. The universe is full of photons and some hadrons like protons, neutrons, which were produced by the quarks. Most of the quarks were annihilated or converted into these hadrons. Now electrons and their antimatter counterparts, positrons, were being produced in pairs from photons combining together in a process called pair production. These were the leptons, electrons and their counterpart positrons, as well as muons and antimuons. They began to dominate during this time. As the universe expanded, the universe got too cool for muons and antimuons to be produced anymore because they're a bit heavier than electrons. They hence require more energy to produce versus the electrons. So muons were a quick thing. Today, the only muons that exist are in the Earth's atmosphere when cosmic rays collide with them and create muons and antimuons, but they quickly annihilate or decay, as well as in particle accelerators where you can create these muons. They only exist for a couple microseconds as they decay quickly into electrons and neutrinos. But 10 seconds into the universe, it cooled further past the threshold by which electron-positron pairs could be produced. So now those begin to die out and annihilate each other. However, electrons win the battle with the positrons because of an asymmetry in the early universe during leptogenesis when these leptons are being produced. So we were left with a surplus of electrons, about as many electrons as protons. And now we enter the Nucleosynthesis epoch, about 3 minutes into the universe. Now the universe cools down to about 100 million degrees and is about thousands of light years across. By now, the universe's expansion is no longer exponential like it was in the inflationary times. Now it's still expanding, but at a slower rate. And now we have the right ingredients to make atoms. However, they weren't forming during this time because photons would just break them apart anytime they tried to. So there are no atoms yet, but there are the building blocks for heavier atoms, like deuterium nuclei, which consist of 1 proton, 1 neutron. And once these deuterium nuclei form, they combine with other nuclei and form larger nuclei like helium, lithium, and even beryllium nuclei. Remember, we've had hydrogen nuclei for a long time because that's just 1 proton. But still, the temperature of the universe was too high for these nuclei to capture electrons and form stable atoms. So what we have now is just a soup of atomic nuclei, electrons, and photons. 20 minutes after T = 0 and Big Bang nucleosynthesis ends. All those nuclei stop being produced. The universe is too cold for widespread fusion. And now we're left with a universe that consists of mostly hydrogen nuclei, 75%, and helium nuclei, about 25%, and other trace nuclei. And this leads us into the photon epoch. Here, the observable universe is now 1 million light years across and 1 million degrees. Photons are still the dominant energy in the universe. There's comparatively little matter in the universe. And you still can't see through the universe. It's still this white, opaque plasma that's just glowing all around you. You can't see anything except for the plasma. But by 60,000 years after T = 0, photons begin to lose energy as they stretch with the expansion of the universe. And now matter begins to dominate over the photons in terms of energy. And now there are different pockets of space throughout the universe with varying degrees of matter in them. So now there are differences in densities. So there are pockets of space that are less dense, they expand faster than pockets of space with more matter. Matter kind of slows the expansion of the universe in those pockets. So now we start to see the density fluctuations grow and increase with gravity over time. And these initial fluctuations of densities were caused initially by those quantum fluctuations. In 380,000 years after t equals 0, we finally get to the Recombination epoch, where a crucial 3000 Kelvin is reached throughout the universe, or about 2700 degrees Celsius. And now the temperatures are cold enough for those atomic nuclei to capture their electrons and neutralize into stable hydrogen and helium atoms, the first atoms of the universe. And for the longest time, those photons were trapped throughout the universe, scattering off of electrons and protons. They couldn't escape anywhere. But now for the first time, those photons could decouple. They could freely escape into the universe. And now the first light can be seen throughout space and time. This is the first true light in the universe that we can see today with telescopes. This light is the light from the cosmic microwave background, the first baby picture of the universe that we have. Now, in the early universe, remember those photons were X-rays, gamma rays, then they shifted down into ultraviolet, infrared, and today, because as the universe expanded, that light decreased in energy, we see it as a microwave form. But back then it was in gamma and X-ray form. And these photons are traveling all around you. There's photons right now inside of your room, inside your house, inside your body. There are photons all around us. This is the smoking gun evidence of the Big Bang itself. You and me are the first generations of humans to see and observe and understand this. All this leads us into the cosmic dark ages. Welcome to the Cosmic Dark Ages, 380,000 years after t equals 0. By now, the universe is full of hydrogen and helium gas. There are no stars, there are no galaxies, there's no sun, there's no earth, there's no life. The universe is dark. 3 million years into the universe's history, all of those photons that had escaped from the Recombination epoch have stretched with the universe's expansion into the infrared spectrum, meaning we couldn't see them. The universe was completely dark during this time. The spots in the universe where baryonic matter was densely populated couldn't collapse yet into stars because the pressure from the photons and the radiation in between them were preventing them from collapsing. However, there's a dark secret I've been keeping from you throughout this series. Dark matter exists with baryonic matter in the universe. In fact, there's way more dark matter than baryonic matter, the stuff we're made of. The special feature it has is that it doesn't interact with photons. It wasn't affected by the pressure from the photons at all, and so dark matter could collapse first and form these seeds by which baryonic matter could collapse into and fall into. So dark matter laid the groundwork for the first stars and galaxies. So as tens of millions of years go by, matter begins clumping together. And as they get denser and denser, the expansion of the universe around them slows down because matter slows down the expansion. And so their density becomes even more exacerbated. They get denser and denser because the expansion of the universe is no longer constraining them by pulling them apart. Now they can collapse even further into very dense clouds of hydrogen and helium. These are called primordial gas clouds. 100 million years after t equals 0, the very first star is born in the universe. As those gas clouds got dense enough, they began to collapse under their own weight. And the pressure inside became so intense that those protons from the hydrogen atoms began to literally fuse together. Now, protons are positively charged. They don't like to be stuck together, but the immense pressure forced them to fuse, and that process creates energy and helium atoms. And helium atoms in those larger stars can fuse together to form carbon. And carbon atoms can form nitrogen, and it goes on until iron. Up until iron, the fusion process generates enough energy to push the star outwards and keep it balanced. There's gravity keeping the star in, and photons and radiation from the inside pushing out, keeping the star balanced. But once iron is produced in the star, it takes more energy than it actually generates. So it actually sucks away energy from the star. And so as the star loses its internal energy source, it starts collapsing on itself. And this collapse is strong enough to generate a supernova explosion, which in itself is brighter and more powerful than several stars put together. So the very first stars were extremely massive, they burned brightly, and they were extremely hot, but this all came with a cost. The cost was a shorter lifespan. Because these stars burned fuel so quickly, they lived maybe only a couple million years. And so the early universe was buzzing with tons of supernovae, stars exploding everywhere, and leaving all their enriched gases and dusts behind, all that stuff full of iron and calcium and hydrogen and helium and carbon, the stuff we're made of, got shot out into the universe, and they formed further stars and stellar nurseries. All of those elements that were produced inside the star got sent out into space and formed further gas and dust clouds, which then recycled into new stars, new generations of stars. Some collapsed and formed black holes, which are going to be important for galaxy formation. And by 300 million years after t equals 0, the first galaxies begin to form. The James Webb Space Telescope has observed a galaxy that is 13.5 billion years old. This is the oldest galaxy we know of. These very first galaxies were very weirdly shaped. They were very irregular, not like today's galaxies. This is because back then, most galaxies were colliding with one another. Remember, the universe was smaller back then, maybe 50 million light years. There was a lot more activity going on. The universe was buzzing with tons of galaxies that were colliding with each other, flying by each other. And this caused the outer arms to get pulled by the flyby galaxies, as well as the collisions merged the two galaxies together. At the center of these galaxies are supermassive black holes that emit these giant jets of radiation that can beam thousands of light years into intergalactic space, affecting other galaxies around them. So we see tons of messy galaxies back then during this time. And as all these stars and galaxies were emitting tons of ultraviolet radiation, it actually stripped away the hydrogen and helium atoms from their electrons. So now they were just neutral atoms, and this turned them into a plasma state. And so the gases in intergalactic space, the gases between galaxies, became ionized again. And this is called the Reionization epoch. And by 1 billion years after t equals 0, the universe is brighter now. It's almost as if somebody turned the lights on to the universe. Now there's tons of galaxies and stars, and the intergalactic medium is ionized. We have a fairly familiar universe. And this leads us into the next episode about galactic clusters. We don't just live in a galaxy, we are part of a much bigger and complex structure in the universe called the cosmic web. 1 billion years after t equals 0, the Milky Way, our galaxy, was in its infancy, and it was beginning to merge with other galaxies around it, becoming bigger and bigger over time. As more and more galaxies formed, they began to eat each other up. They merged together to form bigger and bigger galaxies. The more massive galaxies were enabled by dark matter halos. Dark matter exists all around us in this dark matter halo, this spherical structure around us, and it keeps our galaxy together. All this dark matter also has a net angular momentum, so it actually moves and spins and rotates, and this is what drives the rotation of our galaxies, especially in the outer arms. As these dark matter halos became denser and denser over time, neighboring galaxies became gravitationally bound to these and attracted to them, and so now we have clusters of galaxies form. And then these clusters of galaxies can find other clusters and become gravitationally bound to other clusters, and now we have super clusters of galaxies. These contain hundreds of thousands of galaxies. Now you might be asking, what are these galactic clusters moving towards? Well, remember, it's the dark matter. Dark matter makes up most of the matter in the universe, but you can't see it. And the thing about dark matter is that it doesn't interact with light, nor does it interact with itself, at least very much. And so instead of clumping together like regular matter does, because electromagnetism, other forces get a hold of them, Dark matter doesn't do that. They kind of diffuse and become spread out into these halos that form these spherical spheres around galaxies. Now, when we look out in space, we find that all the clusters of galaxies nearby to us are moving towards a specific direction. They're moving towards something called the Great Attractor. The Great Attractor is a supermassive gravity well that is made up of almost all dark matter. All the galaxies in our supercluster called Laniakea are moving towards the Great Attractor. If you look at a map of our supercluster, you find that all the galaxies are flowing almost like down a stream very slowly towards the gravity well called the Great Attractor. If the Great Attractor is like the river basin of our supercluster, galactic filaments are like the river channels flowing towards the Great Attractor. What holds the cosmic web together are galactic filaments. So think of them like tubes of dark matter, which galaxies can flow like water down a river, flow through one side to the other. So galaxies can move through these galactic filaments that are sometimes hundreds of millions of light years long. Galactic filaments are like the highways of a city connecting one galaxy to another cluster of galaxies. The entire universe is full of these networks of superclusters of galaxies and cosmic filaments, all connecting all of us into this cosmic web. And by 9 billion years after t equals 0, dark energy begins to dominate again in the universe. Dark energy is one of the most mysterious things in the universe. We don't really know what it is, but it seems to be this anti-gravity, this repulsive type of gravity that instead of pulling things together, it pushes them apart. It might be a feature of space and time itself that's pulling and stretching space and time, causing it to expand. Now, matter and gravity tends to want to decrease the intensity of this dark energy. But as the universe continues to expand, dark energy is able to dominate more and more. And so the expansion of the universe is accelerating. Now, there's some evidence showing that dark energy might actually not be a constant throughout time. It might be the case that dark energy's intensity weakens or strengthens over time and evolves. We still don't really know. It's one of the most mysterious things about our universe. But 5 billion years ago, our sun is born, the earth is born, and life begins to evolve. In present day, the universe is about 93 billion light years across. This is the observable universe. What is not observable could be much more than that. And the observable universe contains about 2 trillion galaxies and 10 to the 22 stars. Having gone through 13.8 billion years of cosmic evolution, from a universe that was very dense and hot to a universe that's now just hovering above absolute zero in temperature. How astonishing that the complexity of our universe that we see today is fully explained by 4 fundamental forces mediated by matter and energy within space and time. That's enough to explain all of that we see. And we finally live in a time in which we can understand this. Well, this leads us into the next video where we talk about the future of the universe. What's going to happen to everything in the universe in the future? What's the fate of our universe? Well, in this series finale, I'll explore all the major events happening as far into the future as we can go. Starting with next year, assuming there are no further delays, GTA 6 will finally be released. Then, over a time period of about 500 million years, our sun is going to be about 5% warmer than it is today as it burns hydrogen in its core and it gets denser and denser. So the Earth will be too warm in only 500 million years to support any kind of complex life. The oceans will be warm enough to boil away. And by about 1 billion years from now, the only things on Earth will be extremophiles, bacteria, that can withstand the heat. Then about 4 billion years from now, there's a 50% chance of the Andromeda galaxy colliding with our Milky Way galaxy. Now the Earth won't be physically affected by this. It won't notice the collision because space is too vast. But looking at the night sky, you'll see lots of more stars, assuming anybody's there to see them. Then about 5 billion years from now, the sun is going to start growing in size and engulf planets like Venus, Mercury, and the Earth as it becomes a red giant and it starts burning helium in its core. But over time, the sun as a red giant is going to become unstable, and it's going to start pulsating. And this pulsation is going to eject tons of plasma and the material from its outer layers out into space. And the sun is going to turn into a planetary nebula with a little white dwarf at the center, right? What remains of its core. Then about 1 trillion years from now, as the universe expands further and further, and galaxies that are furthest away from us expand faster away from us, we'll no longer be able to see any galaxies beyond our local cluster. And so the universe will become darker and darker and darker as galaxies move beyond the observable horizon and are no longer able to be observed by us ever again. Then about 100 trillion years from now, the few remaining stars in the universe are going to burn the last of their fuel. So the red dwarfs, the smallest, longest lasting stars, are going to finally die out. And throughout the universe, the only things remaining at this time are going to be black holes, neutron stars, and white dwarfs. Then in about 10 to the 20th years from now, that's 10 with 20 zeros following it, by that time, all the things around galaxies are going to be sucked into their supermassive black holes at the center. So all those white dwarfs and neutron stars are either going to be sucked into their black holes, or they're going to be ejected out into space and forever just be rogue stars. And then in about 10 to the 40th years from now, proton decay occurs. And this assumes that protons are unstable, but by this time, even protons themselves may break down into smaller particles like photons, positrons, electrons. And so anything like stars, any remaining neutron stars, anything like that are going to themselves break down. Then in 10 to the 50th years from now, the first GTA 7 trailer is going to be released. And then 10 to the 100th years from now, that's 10 to the Google years, black holes themselves, all the remaining supermassive black holes, will evaporate away via Hawking radiation. Turns out black holes emit radiation, and over time this decreases their mass, and in a final burst of energy, black holes themselves will vanish away forever. Now beyond this, the universe continues to expand forever and ever and ever, and particles themselves become so far away from each other they can no longer do anything. They can't perform anything together, and so all atomic motion stops. Nothing ever again happens in the universe, and it dies in a heat death. Then shortly after that, they'll announce that GTA 7 will be delayed. Now the alternative scenario is that if dark energy itself weakens, then perhaps the universe will expand but eventually collapse again into a big crunch. And perhaps this big crunch will spark another Big Bang. It's possible. Speculative, but possible. This series may have stirred a bit of existential tension in you as you learn about the vastness of space and time relative to our very small and finite lives here. You start to feel scared of being insignificant in all this, right? And we as humans are very scared to concede even a bit of insignificance, because if we do, that means we're a waste, we're useless, we're invalidated. But that couldn't be further from the truth. In fact, when you do science, when you learn about the universe as revealed to us through science, you come to grips with that insignificance for the first time. You stop running away from it, which is what we've done in the past for centuries. We run away from it, and then that just fosters more fear. But you start facing it, and you let yourself feel insignificant and realize it's not that bad. I'm still here. I'm still breathing. I'm still alive. I'm not invalidated. I'm not wrong for being insignificant, right? And so we've been trained this whole time to think that our significance is tethered to us being accepted by the universe. And so we've contrived these religions and gods and spiritualities to make us feel as if we have to be accepted by somebody to be significant. But when you let go of that expectation, along with the understanding of the universe and the richness of our cosmic history that we all share together, 13.8 billion years of rich cosmic baggage, that's enough. You realize that that's enough. We're all amazing because of that. And so you begin to appreciate the world more and more, and the finitude of our lives is even more precious, even more valuable, because we're finite, because this life is all we have. You realize that in the timeline of our universe, in the immensity of space and time, there's no time like now.